All right, so we're going to mimic the same analysis here. So we're going to first apply the ratio test to AN. So why don't we get started? Okay, so AN in this regard is going to be this whole chunk here. Okay, so I'm going to look at the limit of the absolute value of the ratio n plus 1 over an, right? Here we go. Minus 1 to the power of n plus 2 times x minus 2 to the power of n plus 1. Okay. N plus 1 times 2 to the n plus 1. I'm going to divide it by an, but an is obviously a fraction at the top, as you see. I'm going to flip that over. Okay, how about that? That's going to save a lot of space for us instead of rewriting this, right? All right. As in part B, the alternation is not a big deal when you are doing the operations in absolute value, right? So since you're taking absolute value at the end, it doesn't matter if you have the sign to be negative or positive. It's going to be absorbed anyway. The negative sign is going to be absorbed. So let's continue with simplifying this. Okay. You have x minus 2 to the n, x minus 2. You have n, you have 2 to the n. You have n plus 1, and you have 2 to the n times 2. And you have x minus 2 to the n. So I split 2 to the n plus 1 into 2 to the n times 2 and close the absolute value. Okay, so let's see what cancels out. Well, first of all, x minus 2 to the power of n cancels out. Okay, and 2 to the n cancels out. Okay, so what we're left with is, let's keep the n related term first. N plus 1 times 2, and also x minus 2 absolute value. Again, I isolated the n part from the x part. Okay, so now I'm going to figure out what this limit is. All right, so this is side work, right? You can use the L'Hopital's rule if you want to, and you should convince yourself that this limit is equal to 1/2. So going back to the analysis here, this limit here is going to be equal to the limit of the absolute value of x minus 2 over 2, which is x minus 2 over 2. Okay? And remember, x is a parameter. I'm going to try to determine that, but the ratio test concludes that when the limit is less than 1, when this limit less than 1, then the infinite series here is convergent. Okay, let's sort of follow that through. All right, so this is supposed to be less than 1. Okay, so now I want to understand what this is. Okay, well, x minus 2 in absolute value divided by 2 less than 1 means this. So why don't we multiply both sides by 2 first? Then the absolute value of x minus 2 is strictly less than 2, which essentially means that x minus 2 is in between negative 2 and 2. By adding 2 to both sides takes you to a nice interval for x. Okay, so the interval of convergency as an immediate conclusion is 0 and 4. Okay, but we have to analyze for the endpoints. We have to analyze the infinite series for the endpoints. So what I'm going to do next is to analyze the case x equals 0 and x equals 4. Okay. Let's go back to the description of the infinite series, and for x equals 0, this is the sum, and starting from 1 to infinity, minus 1 to the n plus 1. When x equals 0, this is minus 2 to the n. All right. and the bottom, right? N times 2 to the n. Okay. And for x equals 4, I'm going to keep the rest the same. And I'm going to check what x equals 4 corresponds to. And x equals 4 here. 4 minus 2 equals 2 to the power of n. Okay? Well, there's going to be some cancellations here, and we're going to be very careful. Okay? So first of all, this 2 to the n is similar to this one, minus 2 to the n. Let's just expand this out. So this is equal to, I'm going to split the base and write it as like minus 1 to the n and 2 to the n. Because when the exponents are the same, you can multiply the bases. That's how you get to the minus 2 to the n. But what writing it this way allows me to cancel out, right? To cancel out, let me use a different color here. 2 to the n and 2 to the n. Okay? And here on the right, these are already canceled out. Okay? All right, so I rewrote those expressions. One observation here is that, so going back to here, so these two terms added up to minus 1 to do 2n plus 1. That makes it, in fact, negative 1 because you're talking about odd powers of negative 1, right? No matter what n is. So this series is, in fact, minus 1 over n. There's no alternation anymore. Whereas this one keeps the alternation here, right? There's an alternation here. All right, the first series is a known series. So this is a p series for p equals 1, or simply it's a harmonic series. We know that when p equals 1, the series is divergent. Okay, so we know that this is divergent. Okay, and this is an alternating series. We have alternating series test to apply. So for a n equals 1 over n, which is the non-alternating part of the series, okay, we have two conditions to check. Limit of a n is supposed to be 0, which is the case, and a n plus 1 should be less than or equal to a n, so a n should be a decreasing sequence, but that's obvious. 1 over n plus 1 is always less than 1 over n, okay? You don't even need to have the equality sign here, okay? So, and that's true. That implies ANs are decreasing, okay? So two conditions are satisfied. Okay, I can go ahead and then conclude that this case gives us convergency. Okay. X equals 0 is divergent, and x equals 4 is convergent. Going back to our analysis here, I can in fact touch up this interval here that I came up with. So first of all, we add x equals 4 as a convergent case, so I can add the equality sign here. I can't add the equality sign for x equals 0, so the interval is going to be open on the left and closed on the right. So that's the interval of convergency. In fact, I can go back to the original problem and write the interval of convergency as 0, 4, closed on the right. Okay. And for part D, please watch the next video.